In this tutorial, we're going to see how the LMS adaptive filter can be used for the adaptive system identification of simple two-gene regulatory network, X activates Y. So here we have a cell and there are two proteins, X and protein Y. We measure protein concentration over time, and this is concentration. You may have X here like this. Y will increase and reach a steady state. Since we will not be doing this experiment, we will simulate. An equation for that is this. Y of I is equal to A1 of I, X of I minus 1 plus B sub 1 of I times Y of I minus 1. And we need equation for X as well. X of I is X of I minus 1. Because X protein level is a constant, we will have this equation. But we will add some noise to X. That's why we observe these fluctuations for X. And also we will add the noise to Y as well. This X of Y and Y of I, or X of Y minus 1, these are measured data. And for our system identification, we will have a model which is this. Y of I hat is equal to A sub 1 of I hat times X of I minus 1 plus B sub 1 of I hat Y of I minus 1. This value, they are measured values. So these values will come from these equations. On the other hand, these values are estimated values. And our goal is to estimate these perimeter values, which minimizes the error. E of I, Y of I minus Y of I hat. And this Y of I hat is this one here. And this Y of I is this one here. Our LMS adaptive filter is this. W opt of I plus 1 is equal to W opt of I plus mu times data vector T of I, E of I. And what is W opt of I? It's a vector. A sub 1 of I hat and B sub 1 of I hat. And what is this data vector T of I? This is also a vector. X of I minus 1, Y of I minus 1. And we can rewrite this like this. A1, I plus 1 hat, B sub 1 of I plus 1 hat is equal to A sub 1 of I, B sub 1 of I plus mu times data vector T of I is X of I minus 1, Y of I minus 1. And this EI is Y of I minus Y of I hat. So this goes here, and this goes here, and this one goes here, and also here. So this tells us that if all these are available at time I, then you can estimate future or the next perimeter values. So these are the steps that we need to follow for the simulation. The first step is the initialization step for the estimated perimeter. There can be some other values that are close to these real perimeter values, but here we will start from 0. And note that this is executed only once initially. Now in step 2, we find out Y of I hat using this equation here. In step 3, we find out E of I using this equation here. And at step 4, we find out A sub 1 I plus 1 and B sub 1 I plus 1 hat using this equation. And then we go back to step 2. And these 3 steps are repeated over and over. So these are iterative steps. Lastly, this equation here can be decoupled into 2 separate equations. So A sub 1 of I plus 1 is equal to A sub 1 of I plus mu times X I minus 1 times Y of I minus Y of I hat. And the second equation is B sub 1 of I plus 1 is equal to B sub 1 of I hat plus mu times Y of I minus 1 times Y of I minus Y of I hat. And we're going to use these equations for the simulation. This code has one for loop, and this for loop has two parts. The first part is for simulated experiment, and the second part is for adaptive system identification, which uses LMS. In the first part, measured X and Y protein concentration values are generated, which are of course simulated using these equations. Note that we are adding this random noise to each value. In the second part, first we find y hat of I, and then using this value, which is y of I here, generated previously, and by having this y of I subtracted by y hat of I, which is this one here, we find the error, Y protein estimation error. Using this stochastic gradient descent method, we find next A1 hat and B1 hat values. And let me explain what we have here. This part is for simulated experiment. We assume that X protein levels are constant, which is 5 micromolar. We assume that A1 is 0.2 and B1 is 0.9. And this M, which stands for mean of Gaussian noise, and SD, standard deviation of Gaussian noise, are used for creating this random noise. If you look at this for loop here, I goes from 1 up to n minus 2 because this number is not included. The reason it goes from 1 is that because we have this I minus 1 discrete time index expression. If this I starts from 0, then 0 minus 1 becomes minus 1, which is not available. Our discrete time index starts from 0 by convention. But the problem is, since it starts from 1, we don't have value for x of 0 and y of 0. So that's why we need these two lines of code. And likewise, this I goes up to n minus 1, not n, because of this term here. If I goes up to n, so if you put n here, that means I goes from 1 to n minus 1. And if you have this discrete time index I plus 1, that will become n, which is beyond our range allowed. That's why we have n minus 1 here. Since this for loop will stop before generating the last measured and estimated values, we have these extra lines of code to find out those missing values. Let me run the code and see the results. Okay, maybe once more, one more. So you see that every time I run the code, I see somewhat different results, but basically they are showing us the same thing. This yellow line represents X protein concentration. This green line represents Y protein concentration. And this blue line is estimated Y protein concentration. Red line is the difference between green and blue. So it's the difference between Y protein and estimated Y protein concentrations. Initially, we have large errors, but as the filter learns more, the error decreases and converges. And we have estimated A1 here, which is purple. And also we have estimated B1. So let me zoom in so that we can better see those estimated perimeter values. Okay, let me run the code again. So let me type in A1 hat. So A1 hat, which is this line here, is about 0.53, right? If you remember, we assume that this A1 is 0.2 and our estimated A1 is about 0.53. So you see that there is some difference, estimation error. This is a perimeter estimation error, which is different from this Y protein estimation error. B1 hat is 0.72 something. And again, we assume this B1 to be 0.9. So there are some differences. So using our LMS filter, these are estimated perimeter values.